Serotonin is a neurotransmitter, a chemical messenger in the brain by which neurons communicate with one another. As serotonin molecules leave the end of a presynaptic cell via vesicles, they are released into the synaptic cleft between two neurons. These molecules can then bind to receptor proteins embedded in the plasma membrane of the postsynaptic neuron, allowing for ions to pass through the cell membrane and changing the electrical state of the receiving neuron in the process. Once neurotransmission has completed, serotonin molecules in the synaptic cleft undergo reuptake, whereby the presynaptic neuron reabsorbs the molecules for recycling via receptor proteins called serotonin reuptake transporters, or SERTs. This incredibly important process is made possible by chemistry, specifically by way of intermolecular forces between molecules of serotonin and those of the serotonin receptor. For a molecular drug to bind to a receptor, it must have a specific structure that fits into the protein. In other words, it must be able to interact with the molecules in the receptor via intermolecular forces. Since receptor proteins are covalent molecules and most are polar, having slightly positive regions and slightly negative regions that depend on the particular amino acids present, an electrostatic attraction can allow a neurotransmitter to interact with the compatible receptor. Accordingly, serotonin is able to bind with receptors embedded in the plasma membrane of a neuron due to its polarity. Various dipole moments are present due to the unequal sharing of electrons in its functional groups. For example, in its hydroxyl group, the oxygen atom is much more electronegative than the hydrogen atom, and the covalently bonded electrons therefore are more attracted to the oxygen than they are to the hydrogen, causing a separation of charge that allows the group to interact with other polar molecules or regions. In addition to these dipole-dipole interactions which result from the partial charges, this functional group enables serotonin to moreover undergo hydrogen bonding with other molecules that have a hydrogen bonded to a highly electronegative atom. The core of the serotonin molecule is formed by an indole ring, which is made up of two carbon-based rings that are joined together. The ring is aromatic, meaning it is formed by sp2 planar carbon atoms. Indoles have great electronegative potential since there is a lone pair of electrons on the nitrogen that are perpendicular to the pi bonds of the aromatic system, and thus these electrons are able to form bonds. However, the indole consists of a benzene ring fused with the pyrrole ring. And benzene is a nonpolar molecule since it is a hydrocarbon with mainly nonpolar bonds, or bonds with relatively small dipole moments that ultimately cancel due to the symmetry of the ring. Consequently, serotonin is also capable of undergoing hydrophobic interactions due to this nonpolar center. Hydrocarbons are usually nonpolar and insoluble in water, as carbon and hydrogen have similar electronegativities. But because of its polar functional groups, such as the hydroxyl group, serotonin is soluble in water, allowing it to circulate the body through the bloodstream. The binding of serotonin to the serotonin receptor is what allows the neurotransmitter to have an impact on the human body. Reuptake by the presynaptic neuron can cause serotonin concentrations in the brain to drop, and research has shown that low levels of serotonin, the happy chemical, are associated with mental illnesses such as depression as well as decreased concentration and mood regulation overall. Accordingly, when serotonin levels are low, a medical professional may prescribe an antidepressant to help alleviate excessive and/or persistent sadness. Some of the most common prescriptions are selective serotonin reuptake inhibitors, or SSRIs. As the name suggests, SSRIs are selective due to their unique molecular structure, and more importantly, they inhibit the presynaptic neuron from reabsorbing serotonin, thereby increasing levels of serotonin in the synaptic cleft. Just like serotonin, SSRIs are able to bind to certain receptors, in this case blocking reuptake pumps, through their intermolecular interactions with the proteins embedded in the plasma membrane of the neuron. In order to understand how these forces contribute to SSRI function, let's analyze the structure of the most recognizable and used SSRI, fluoxetine. Fluoxetine has 7 specific functional groups, as shown here. These functional groups influence the molecule's water/lipid solubility, ability to interact with certain biological targets and receptors, mechanism and duration of action, route of administration and metabolism, as well as other drug interactions and side effects. As can be seen from fluoxetine's molecular structure, fluoxetine has hydrocarbon chains that are nonpolar. This may seem counterintuitive since receptor protein amino acids often have molecules with dipole moments and are thus polar. Consequently, it would be expected that fluoxetine, a mostly nonpolar molecule, would not be able to interact much with serotonin reuptake transport proteins. However, drug manufacturers deliberately add hydrochloric acid to fluoxetine, increasing the polar character of the molecule in the process. We can explore how HCl increases polarity for lipophilic drugs by examining the secondary amine group on the fluoxetine molecule. This functional group, comprised of nitrogen and hydrogen, has a protonation site. The amine can exist in its charged form when the nitrogen atom forms one more hydrogen bond with the hydrogen from HCl. This electrostatic attraction has enough strength to allow the drug fluoxetine hydrochloride to come closer to and interact with the polar regions of the presynaptic serotonin receptor. And as the protonation of the amine group increases the molecule's polarity, the addition of HCl provides other benefits, such as allowing the ionic compound to dissolve readily in blood as well. What ultimately keeps the drug-receptor combination stable, however, is hydrogen bonding. As the fluoxetine approach the receptor molecules, they can form multiple hydrogen bonds, and altogether these attractions increase the strength and stability of the interactions considerably. Hydrogen bonding furthermore allows the drug-receptor binding to be reversible. This intermolecular force is quite strong when present in large numbers, but it has about 1/10 of the strength of a covalent bond. Therefore, if covalent interactions occurred between a drug and its target instead of hydrogen bonding, electrons would be shared between two atoms, resulting in nearly irreversible binding. This is evidently disadvantageous since it would block off reuptake receptors and thus increase serotonin concentration permanently, which could culminate in severe serotonin syndrome, a condition that could lead to death if left untreated. Overall, the binding of fluoxetine to serotonin receptors via strong, but not too strong, intermolecular forces allow the drug to prevent presynaptic neurons from reabsorbing serotonin, thereby increasing the amount of serotonin in the synaptic cleft. In this way, the SSRI allows more serotonin to be available to improve neurotransmission. With higher serotonin concentration in the brain, the happy chemical can do its work, improving the lives of those whose depression or anxiety interfere with everyday activities. This is especially important in times of unprecedented stress and uncertainty, when depression and suicide rates are increasing unlike no other. For those struggling with their mental health, areas of the brain that are important in mood regulation do not function properly. As such, SSRIs have become a powerful and transformative treatment for those with psychiatric conditions, ultimately made possible by the world of chemical interactions that occur in our minds every single day.